In this video, we'll discuss various paradigms of programming languages. So paradigms are essentially language styles. They're loose classifications or groupings of languages based on things like the language features or the focus of the design in that language or even the execution model of the language itself. Now these are not strict rule sets, but they're more guidelines for when a language should or should not be included or considered to be in one of these various paradigms. It also should be said that paradigms are not mutually exclusive. Languages can fall into multiple different paradigms simultaneously. And the things that you can do in one paradigm, you can likely do in another, though perhaps not as readily. Some languages may be more well designed for solving certain problems than others. Now, the main division when we're talking about paradigms is between imperative and declarative. So roughly speaking, the declarative languages focus on what the computer should do, whereas imperative languages focus on how the computer should do it. So let's go through a bunch of these different paradigms in turn, starting with the imperative class of paradigms. So imperative paradigms or imperative languages focus on statements that control the flow of execution. They say things like do this, then do this, then do this. They also have a focus on the mutations of states, so say assignment operations. Set x to this value, set it to another value, mutate it again and again and again. So computation in an imperative language is the mutation of state in machine memory step by step until some sort of solution is reached. Now, imperative languages model the hardware of modern machines very closely. They follow the von Neumann model, which essentially says fetch, decode, and then execute. That is to say, get one instruction from memory, execute it, and then get the next instruction. So repeat, 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 do this, and then do this. So examples of imperative languages, there's a lot of them out there, but assembly languages, C and Ada would also be considered imperative languages. Also, Fortran and early BASIC with their go-tos are considered imperative languages as well. Now, as I mentioned, imperative is sort of an umbrella of other paradigms. It's sort of a top-level paradigm, if you want to call it that. And within the imperative sphere, we could say, are a number of other paradigms, including, first of all, the procedural paradigm. So procedural is a type of imperative programming which emphasizes organization into subroutines and modules. So it provides modularity to code by having scope. Okay, so it's the idea of having functions and local variables. So this improves code reuse and maintainability, as I'm sure you're aware, having programmed in many of these types of languages yourselves. So procedural and imperative are often used as synonyms, because nowadays if you do have an imperative language, you're probably going to include subroutines in that language. So procedural languages and imperative languages are oftentimes used as the same word. Right, so languages that fall into this procedural paradigm, again, we could say the C language as well as Pascal and BASIC. Right, if we want to compare procedural to something that would be imperative and not procedural, that would essentially be early assembly languages that didn't have blocks of code. The idea is the imperative would have either a single algorithm or the complete functionality written sort of linearly step by step into memory, whereas in procedural languages that structure can focus on procedures and modules, and say libraries of code. So reusable blocks of code comes in when we talk about procedural paradigms. Now, another important imperative paradigm is the object-oriented programming paradigm. So the idea here is that we have, again, imperative programming, so a focus on changes of state, but we also want to focus on interacting encapsulations of that state. So the state in the object-oriented programming is essentially grouped together with behavior into these objects, and that state should essentially only ever be modified by those behaviors that they're grouped with. So this facilitates code reuse through inheritance and polymorphism and a number of other useful object-oriented features, and lets us create these complex hierarchies of objects. So it's pretty distinct from assembly language, let's say, but it still focuses on this notion that we're storing some values in memory, accessing those values, changing them, and storing them again. So mutations of state as computation. So languages in this paradigm would include Java, C++, Delphi, Python, lots of other languages out there as well. All right, so that's the general idea behind the imperative paradigm, and up to this point you might just be thinking I'm talking about programming itself, because if you've never programmed outside of the imperative paradigm, that can just seem like that's all there is to programming. But on the other side of the coin, there's what's known as declarative programming. So the declarative paradigm has a somewhat muddy definition. In fact, sometimes it can be called as simply anything that's not imperative. If we have a program a programming language that's focus is not on the mutations of state, then we can typically say that that's not imperative, so we'll call it declarative. So the general intent of a declarative paradigm language is to focus on describing the outcomes of what one wants, not the process of how to get there. Okay, so the program doesn't describe the sequence of variable mutations. Instead, it describes what the end result of all of that should be. So the programmer's job is to describe the what in terms of the domain, and the how is left to the underlying language implementation. But it's very important to notice here, then, that all declarative languages have to be built on top of an imperative abstraction. The reason being we have imperative machines. We have fixed state memory that can be mutated through time. And even if we can create a declarative language on top of that, the machine itself still needs to follow this imperative fetch, decode, execute cycle. So all declarative languages are going to be built on top of an abstraction over an imperative machine. So by way of analogy, if we want to consider the difference between declarative and imperative, you could think of a declarative language as essentially a car with an automatic transmission, and an imperative language as a car with a manual transmission. So both do the same thing under the hood, but sort of the mechanics of how it's done in a declarative language is sort of automatically maintained for the programmer, whereas in an imperative language we're saying do this, then do this, then do this, change this specific gear now. So one key feature that distinguishes these two things is known as referential transparency. So referential transparency, put simply, means that the variables don't change over time. So the references, the variables, the bindings between a name and a value, essentially are transparent to the programmer. So the meaning of an expression is effectively independent of the order of expressions in a declarative language. So if our values don't change over time, if I say x at the top of my program and I say x at the bottom of my program, if we have referential transparency, which means that those variables aren't changing, then those two x's should have the same value. Essentially, all variables, when we have referential transparency, are just constants. So examples of declarative languages are all of the logic programming languages, the functional programming languages, and other things like regular expressions, database query languages like SQL, as well as HTML and CSS. These are declarations of things that we want to have happen, but we don't need to describe the underlying how they happen. All right, so let's talk about some of these sub-paradigms. So starting with the logic programming paradigm, when we're creating a logic program, essentially we start with a declarative knowledge base. We say, here's what we know about the world. It's a bunch of facts and rules about the domain itself. Okay, so they're essentially statements that are assumed to be true or asserted to be true about the universe as we know it. Okay, and then these are expressed as essentially combinations of logical symbols and relations between one another. So it can relate different facts or different rules to one another as needed. Now, computation in a logic programming language is performed in response to queries. So once we have this knowledge base, the programmer then specifies some goals to evaluate, to ask things like, is this statement true? Or for what values is this statement true? And then the language implementation will determine the process of solving that query. So the how of getting from the question to the answer is controlled by the underlying language implementation, not the programmer themselves. All the programmer has to do is design the universe, the knowledge base, and then query that knowledge base to find out truth values, or answers to truth values, if you will. Okay. So one example language of this paradigm is Prolog, which we'll be covering later on in this course. Okay, another kind of declarative programming paradigm is the functional programming paradigm. So functional is not to be confused with procedural. A lot of times we'll use the term function and procedure interchangeably in this course. But when we're talking about paradigms, the functional paradigm refers to functional programming, but the procedural paradigm refers to a sort of imperative programming that uses procedures, as we've seen before. So with functional programming, the idea is that we're not talking about functions as blocks of code, but rather functions in the mathematical sense. That is to say, a mapping from inputs to outputs, or a sort of relation between the sets that maps every input to some specific output. Okay. So programs in the functional paradigm describe functional transformations, this sort of input to output mapping with no side effects. So a pure function if we give it the same inputs, we'll get the same outputs. It's not dependent on mutable state outside of that function. So there's no side effects that if we run this function once, it's going to change a variable, and if we run it a second time, now it's going to have different behavior. With pure functions, if we give it the same inputs, we get the same outputs. And we can rely on this referential transparency to assert that our values won't change over time. Okay, so in functional programming, computation is done as evaluation of function applications on specific inputs. So I write some function, something like fn here. I apply that to some set of data. That gives me back some sort of result. And then I can apply other functions and apply other functions and apply other functions to the results of those things. So we get this chain of functional transformations. So we start from our input data, and the result at the end would be the output, or the return statement, if you will, of the final call of that function. So all computation is essentially done as the application of functions onto their data. So there's a number of key features that arise in functional programming. The first off is that pure functional languages, at least, avoid mutation of state, as I've mentioned. So variables are effectively bound once created and not mutated. So these variables become effectively constants, if you will. Another key feature is that functions are treated as data. So we have the idea of first class and higher order functions, topics that we'll cover in the coming lectures. So once we treat functions as data in a functional language, then we can start passing the code itself into other parts of the code. And it can be a very powerful feature, as we'll see. So a number of examples of functional languages exist, such as Lisp and Scheme, which we'll be covering in this course, as well as Haskell and many, many others. Now, these are the main paradigms, but a lot of other paradigms exist, and not all paradigms are going to fall in this declarative imperative spectrum. So again, languages can belong to more than one paradigm. So Python and Java are very good examples of so-called blended languages that sort of accumulate features from a number of different paradigms. Java, for example, just recently, a while ago now, has added in lambda expressions and a number of other functional features that it didn't exist for the first 9 or so iterations of the language. All right, so some other paradigms here. Concurrent programming is one paradigm, and this paradigm is a focus on the division of labor and simultaneous processing, or concurrent processing. So for example, GPU processing with NVIDIA's CUDA platform would be considered a concurrent programming language. Now, the benefits of concurrent programming is that if we have some clever division of labor, we can improve the scalability of our designs. We can overcome the physical limitations of computation by scaling out instead of scaling up, if you will. But there's a number of issues that arise with it as well. It requires programmer overhead to figure out those clever divisions, and a bunch of new problems like race conditions and deadlocks arise when we have multiple processes competing for the same resources. All right, another type of paradigm here is metaprogramming. So in metaprogramming, this refers to programs that can write or modify other programs or even their own program at runtime. So it's essentially programs that treat other programs as first-class data entities within their language. So assembly language programs were inherently reflective because they had to operate on essentially the level of instruction pointers. So as these languages develop more structure, this reflectivity sort of disappeared through time, but it can be reinstated now through a number of specific mechanisms and supportive language libraries. So some examples are things like in Java, you might see java.util.reflect or java.lang.classloader are two built-in features from sort of external Java libraries that allow you to operate on code as though it were essentially data in your program. Similarly, Lisp, the original Lisp, has operations like eval and macros that can take in code as expressions and essentially evaluate those on the fly. So it can develop code during the execution of a program and evaluate that code in that same execution. All right, so that's metaprogramming, programs that can work on other programs. There's event-driven programming, which is programming that essentially proceeds in response to events, whether this is from the user or other programs or other threads. Essentially, when one object changes its data, it may send a message to another computational object or computational entity. So things like GUI design or device drivers or even exception handling facilities, these all operate in sort of response to events. So they could be considered event-driven programming. And lastly, not of all the possible paradigms, but last that we'll cover at least, is visual programming. So visual programming is the idea that we can program without having to rely on text. We can specify a program by graphical interactions. So we can have blocks which are considered some sort of computational entity and connecting lines describing relations. Not to be confused with Microsoft's Visual Studio, which is just a fancy IDE with some runtime visuals. But with visual programming, we have actual code being described using graphical interfaces. This can be actually particularly valuable for dealing with graphical user interfaces. So if we want to create some sort of tricky button and widget layout for some end user, it can be a lot easier to just sort of design that manually and then connect the buttons to some underlying code in the background. So things like Xcode Storyboard or NetBeans GUI Builder, which I don't think actually exists anymore. These are examples of sort of visual programming. But a lot of other places visual programming arises, like in video game engines, for example, have a lot of visual programming components like behavior trees for designing AI behaviors. As well as some teaching languages like Scratch and ToonTalk are ways of approaching programming without having to go through all the scary looking symbols. So as we can see, there's a lot of different ways that we can classify these languages. No one of these paradigms is better than any of the others, but it's a way of discussing the collective features or design choices that these languages have in common. There's also a bunch of different reasons to choose one language versus another language. Though in general, what you're going to ask when you're picking a language is something along the lines of how effective is this language at allowing me, a human, to solve my problem? Now, the term effective there is a bit of a loaded term because things like readability, naturalness, versatility, efficiency, these are all aspects of this notion of how effective can I communicate my problem. But one thing to keep in mind of all of these different aspects is that programming languages are for the communication of human ideas. So to that end, I've compiled a list here of a number of features that make for a good programming language. I'm going to say no one language maximizes all of these different features, but let's quickly skim through this list. So things like readability, writability, these are how well we can read and write, or how well we can understand the code that we're actually constructing. Things like naturalness for application corresponds to how easily I can translate from the design or the domain realm into the actual programming implementation. How seamless is that transition? Things like reliability, validation, portability down here, these all correspond to how easily I can construct and maintain this code. How easy am I going to find my own errors? How easy will it be to test my code to determine if it's robust? Things like, is there support out there for IDEs or community support for all sorts of language features and libraries? All of this feeds into the idea of how easily will I be able to, or how effectively rather, will I be able to solve my problem. So there's lots of different reasons to pick a language. In this course, I've already picked the languages to be Scheme and Prolog. So to start, we'll be studying Scheme, which is a dialect of Lisp. Now, Scheme doesn't fit all of these attributes of a good language. In fact, I would say it fits very few of them. It's hard to read, it's at times very inefficient, it lacks built-in exception handling, number of other reasons that make it quite difficult to learn. But on the plus side of it, it has a very simple syntax and a very consistent general rule of evaluation. This will afford us an opportunity to study these core concepts of combination and abstraction. So as we start from very simple elements in our language and build up to some fairly complex applications, we'll be able to see how combination and abstraction play roles in doing just that. So that's the end of this video. We covered all about programming paradigms here. In the next video, we'll dig into programming in Scheme in Chapter 2. And I will see you there.